We will be doing an exercise which is based on a past paper of 2024 from the chapter developments. So in grade 10 and grade 11, the learners were expected to calculate graphically by means of sketches the true lengths or various true lengths of developments and then to draw the developments as well. Now in grade 12, these true lengths are not drawn but calculated mathematically. So from the given information, there is a square to square hopper which is off center. Okay, so let's quickly go through the terminology from the given information. So if we are given a square to square off center hopper, let's quickly discuss what is a hopper first. A hopper can also be referred to as a type of a funnel. So a funnel normally at the bottom, the opening at the bottom of that figure will be smaller compared to the top surface. So this bottom square, the smaller square will be at the bottom and the top square will be at the top. So this is a square, the bottom surface, square to square hopper, but the center square is off center from the top square. If we draw for ourselves a front view of the hopper, it would look something like this, where, as I mentioned previously, the bottom surface is the smaller square, which is this one here, and the top surface is the bigger square, which is over here at the top. And also what is given is the vertical height, which is 850 millimeters. Okay, so from this given sketch, they ask that we calculate the true length for B3. So that will be the true length of this distance here. Then also the true length for XY, this one here, and the true length for C4, which is this distance here. But keep in mind, all of these are true lengths and not the base lengths. So if we only work on this two-dimensional top view sketch, then we will be calculating firstly the base length of XY, and then we put the base length in proportion with the vertical height which goes up over here, which is 850. And we will use this by means of Pythagoras. The other one also, B3, which is this one here. For this one, we will create a right triangle from the two-dimensional top view, where we have this distance and this distance placed into the Pythagoras theorem, which gives us the base length of B4, and then we put this in proportion with the vertical height. And the last one is the true length for C4, which is this distance here. We will draw a vertical line going up here so that we have a 90-degree triangle when looking at the view from the top on a two-dimensional surface or plane. And then we will take this distance and this distance, put it in the Pythagoras theorem to get the base length C4, and thereafter put that in proportion with a vertical height, which is 850, to get the true length for C4. Okay, so let's start with question number 1. So there are two methods that you can follow to calculate the true length for B3. I will firstly be explaining the longer method, where two separate Pythagoras theorems formulas are calculated, and then we get the final value. Or the shorter version would be to combine two Pythagoras theorems to have three values below the root sign, the square root sign, and then get the answer for the true length. So firstly, to get the true length, we will first have to get the base length of B3. So we will be creating a 90-degree triangle on the top view for ourselves, so that over here we have a 90-degree angle and triangle B3 and this corner here. So first our focus will be to get this base length calculated. To get this base length, we're going to use this width, which is 300, and we will be using this distance from B up to the 90-degree angle, which we will first have to calculate. So to calculate this distance, the value from the top of the triangle, of the big triangle, is 950. 950, so we will write here 950 minus the 350 to give us the distance from here to B. So that will be minus 350, which gives us a value of 600 millimeters. Okay, so we will be using this 300 over here and adding the dimension from there to there is 600 millimeters. Okay, so we are using the 600 millimeters, the 300 millimeters to get this base length, and we are focusing on this triangle firstly. Okay, so we will write down that we are calculating the base length, BL referring to base length, B3 equals to the square root of 300 squared plus 600 squared. And this will give us a value of 670.82 millimeters. Okay, so now that we have calculated the base length of B3, looking at the sketch from the top, now we will put the base length in proportion with the vertical height of 850. So remember, referring to our front view, which looks like this, the vertical height is 850. So we will put this base length of 670 in proportion to the height by means of Pythagoras. So now we say true length B3 equals to the square root of this value, 670.82 millimeters squared, plus the vertical height of 850 millimeters squared, ounces squared, gives us a value of 1082.82 millimeters. Okay, so this will be the final answer for the calculation number 1, but I would like to show you a shorter method of doing this calculation by combining these two Pythagoras theorems into one. So it will be that value, or we will, instead of first working out the base length, we will directly start calculating the true length. So true length B3 equals to the square root of still the two values that we used to get the base length, which is 300 squared plus 600 squared plus these two values together gives us this value, which we placed over here in the next formula, and we just added the vertical height. We put the base length in proportion with the vertical height. So this 850 is written down as a third value under the square root sign, which will give us the same value, 1082.82 millimeters. Okay. The marks are allocated in the following way. 1 mark per value, which is written down under the square root sign. 1 mark will be given in between, as a step in between here, where you write down the sum of all of these values added together, and then also for the final answer over here, which is rounded to 2 decimal places and will give you a total of 5 marks. Next, we will calculate the true length for xy. Xy is this distance over here. Looking at this slanted line from the front, it will be this distance from there to there on a flat surface in front of you. So if you look at this from x, which is at the top, and y, which will be at the bottom, it will form a triangle which looks something very much like this. Okay, so let me just check here. This will be the x value, that will be the y value, where the vertical height is 850, and this width over here will be this width from x to y as the base length. So let's check what is the base length of this xy. The full width is given as 950. So we will say for question number 2, the base length xy equals to this full width of 950 minus 300 minus 400, and xy base length will be what is left. So it's 950 minus 300 minus 400 will give us a value of 250 millimeters. Now we will use this base length xy to get the true length xy, which is the slanted angle. So write down what you are going to calculate. True length TL xy equals to the square root of the base length, the vertical height is 850, plus the base length is 250, which is this distance over here. You can add it in from there to there. And then we will get the slanted value, slanted dimension, which is the true length for xy, which is 250, this one here, equals to plus 250 squared, gives us a value of 886.00 millimeters. Okay, so the mark allocations are given in the following way. It will be 1 mark for calculating the 250, 1 mark for substitution of the 250 into the true length formula, 1 for the vertical height of 850, and 1 for the final answer of 886.00 millimeters, and that's total of 4 marks. The last calculation that we will do will be number 3, where we are to calculate the true length for C4. So we will be doing the shorter version of the Pythagoras theorem, where we put 3 values under the square root sign instead of 2 separate calculations. So true length C4 equals to square root of, now focusing on C4, C4 is this distance here. We will create for ourselves a 90-degree triangle looking at it from the top. So this is a square triangle where the given width of the big triangle is 950 minus 250 will give us a distance of 700. So from there to there is 700 millimeters. The vertical height over here, focusing on this triangle, is 350. And then we can use these 2 values to get the base length C4, and thereafter we will put this in proportion with the vertical height, which is 850. So the 3 values that we require under the square root sign is the 700 millimeters plus the 350 millimeters squared plus the vertical height, which is 850 squared. Which gives us a value of 1155.42 millimeters. Okay, and the mark allocations are given the following way. So 1 for the 750 squared, 350 squared, 850 squared. All of these together under the square root sign will give us, just have a look here, 700 squared plus 350 squared plus 850 squared. So let's just show you exactly where that mark is given. Is equal to square root of 1335000, which equals to 1155.42 millimeters. So the 4th mark is given for the sum of all of these values under the square root sign, and the final one, point number 5, is given for the final answer rounded to 2 decimal places. It is fine if you do not show this step as long as this value is correct. So normally these 3 will be given marks first, and if this one is correct, then automatically you'll get the mark for that one. So this entire exercise counts a total of 14 marks.